I am very excited to be here online from the University Park campus of the Pennsylvania State University. As you know, that traditional manufacturing processes evolved at the crossroad of mechanical engineering and materials engineering. But advanced manufacturing processes also need help from the emerging digital tools such as machine learning and mechanistic modeling. The manufacturing process that got the most benefit from these digital tools is additive manufacturing. So in my talk, I am going to talk about how to control the structure, properties, and defects in additive manufacturing using these digital tools such as mechanistic modeling and machine learning. So I will briefly introduce what is metal additive manufacturing, what are the uniqueness and opportunities that we have in additive manufacturing, and why we need emerging digital tools. In addition, I am going to give several examples of how to use these digital tools to control structure, properties, and defects. And then I would like to point out several major contributions, and I would finish with some future perspectives and broad impacts. As you know that additive manufacturing process is a layer by layer process where thin layers of metals, often thinner than human hair, are deposited, selectively melted and solidified to make a part in 3D. So depending on how we are supplying the material and what type of heat source we are using for melting those, there are mainly three types of metal additive manufacturing process. So in directed energy deposition laser process, the material is supplied in the form of powder, and as a heat source we use laser beam. Directed energy deposition gas metal arc uses consumable metallic wire as the feedstock, and one high power arc is used for melting the material. But in contrast, in powder bed laser process, you can see that very small powders, often in size of microns, are deposited in a powder bed in thin layers, and they are selectively melted by a laser beam. And the process continues until the part is made in 3D. So here I have a video that I'd like to play to show actually how the process works. So you can see that at the very beginning, one thin layer of powder is deposited using a roller, and the laser beam selectively scans the powder bed to melt the material, and eventually that solidifies to make the part in 3D. And this process repeats itself until the entire part is printed in 3D. So this process is very unique. For example, few years ago in the International Space Station, they needed a wrench for some repair purpose. But that time, NASA did not plan for any mission for supplying the necessary commodities to International Space Station. So what they did, they created a 3D design of the wrench, and they sent that from Houston, Texas to International Space Station. And in the International Space Station, they had a 3D printer that printed the fully functional wrench. So even 20 years ago, it was a science fiction. But now, because of 3D printing, it is actually happening in reality. At Penn State, we discovered that instead of having dissimilar materials joint that are used in power plant, let's say a dissimilar joint between steel and a nickel alloy 800H, replacing those joints by graded material where the composition is gradually changing from one material to other material, and we have shown that it significantly improved the mechanical properties such as high temperature creep properties for those joints. And also, I am aware of the indigenous 3D printer that IIT Jodhpur has for printing different type of material parts for aerospace and diverse industries. So you can appreciate that the revenue for additively manufactured parts are coming from diverse industries, starting from consumer product, automotive, marine, aerospace, healthcare, so on and so forth. So what are the problems? Among more than 5,000 commercial alloys that we have now, only a handful can be additively manufactured. And why that is so? Because still we do not successfully control the structure, properties, and defects. So, what do I mean by structure, properties, and defects? Let's say one additively manufactured metallic parts can have two type of solidification morphology generally. One is columnar, the other one is equiaxed. So now you imagine that you are pulling this part in the horizontal direction, and these long columnar grains may start separating from the grain boundary. That means it will have very weak tensile strength. So instead of having columnar grains, the better route is having equiax grains to improve the property. How to get that? We will show. Not only the solidification morphology, the mechanical properties such as hardness also depend on local microstructure, like what are the phases that form. And you can see from this picture that mechanical properties such as hardness vary significantly with distance. So this kind of property inhomogeneity can significantly impact on the serviceability and reliability of additively manufactured part. And most importantly, several common defects such as lack of fusion, surface roughness, cracking, so on and so forth. So, defects such as lack of fusion, they also significantly affect the tensile mechanical properties. You do not want to have your printed part looking like Swiss cheese. That is very undesirable. Surface roughness, people may argue that you can do post-process machining or post-process grinding to achieve a better surface finish. But imagine you are printing a part that has internal cooling channel. How you can get a good surface finish because you cannot do machining or grinding for those internal channel. So your part has to be such so that you have very high surface finish without doing an expensive and time consuming post process machining or grinding operation. So why we need mechanistic modeling and machine learning? I am going to give you two reasons. So as you know that there are many variables that we can adjust during the experiment, like laser power, scanning speed, beam radius, layer thickness, so on and so forth. So I have listed 12 variables, 12 such variables. So even if you follow a two-factor design of experiment, you can see the minimum number of experiments that we need to do to fully understand what works and what does not work is 4096. Now, even if you do one successful experiment a day, a PhD student cannot graduate in 10 years. So that's not a viable route. Second reason, if I take two main variables, laser power and scanning speed, and plot them for different process for same material, you can see they vary significantly depending on which additive manufacturing process you are using. Please note the logarithmic scale. So the laser power for directed energy deposition gas metal arc is almost two order of magnitude higher than powder bed fusion. So we need to explore a very wide process parameter window, and having a machine that is like $1 million and having the feedstock, powder feedstock, which is very expensive, we do not have the luxury to do so many trial and error. But in contrast, The digital tools such as modeling, machine learning, analysis of experimental data can tell us what works and what does not work before doing the experiment. So it can effectively reduce the parameter space, minimize the trial and error, and improve the quality. So that's the viable alternative. So there are two routes. We do the experiments and know what are the process conditions, what are the material properties that we want to use, and based on the underlying physical principle, we develop mechanistic modeling that capture the additive manufacturing process and also the evolution of microstructure, properties, and defect formation. So the benefit is definitely it can give us the variables that affect the attributes of the product. Also, it provides the scientific insight of the process itself and the evolution of structure and property. And most importantly, what we need, it can guide the experiment by selecting the appropriate process conditions to achieve the desired microstructure, properties, and minimize the defect. But also there is a problem. Additive manufacturing is a relatively new process for which we often do not understand the physics for all cases. So what to do? We cannot develop model if we do not understand the physics. In those cases, we take the benefit of data-driven tools such as machine learning. So what we can do, we can take the variables from experiment like process variables, alloy properties, and we can calculate some variables that we know for sure from the mechanistic modeling and then train machine learning algorithms like neural network, random forest, decision tree, so on and so forth. Benefits: it does not need an in-depth phenomenological understanding and it can do reliable prediction even sometimes with less amount of data. But the most important benefit is it can provide the hierarchical importance of important variables. So we engineers can know which variables we need to adjust so that we can achieve the desired product attributes. So before I can give you several examples how to control structure, properties, and defect, let me briefly introduce what do I mean by mechanistic model. So this is a simple additive manufacturing process where you are building a thin wall on a top of a substrate. So the solution domain consists of the substrate, the deposited layer, the depositing material, and the powder. So you discretize it using finite element or finite difference or finite volume into small control volume, which is a cell, and then solve many equations like conservation equations of mass, momentum, and energy. For example, Navier-Stokes equation, Fourier's equation of heat conduction. And then the model takes the process parameters and material properties as input and provides us temperature and velocity fields in 3D, cooling rates, solidification parameters, practically anything you need for predicting microstructure, properties, and defects. Now you can tell me that, Tuhin, it looks like this is very computationally expensive. How I can run it? So let me give you one example. Let's say you are depositing 1 centimeter long track. That's your solution domain. That typically has around 250,000 cells. Cell means these small control volumes. And you are solving for five main variables. Three component of velocities, velocity of the molten liquid, pressure, and enthalpy from which we can calculate the temperature. So at the end, you are solving around 1.25 million algebraic equations. And it's a numerical solution, so you need to do iterative calculation for getting a good convergence. So let's say you are doing 100 iteration, so at the end it's 0.125 billion equations. And just imagine that laser is moving from this location to that location. It's a continuous process. But we need to discretize this continuous movement, let's say into 1,000 time steps. So at the end, you are solving 125 billion equations. It's a lot of equations, right? But at Penn State, we have developed computationally efficient algorithms so that we can solve these 125 billion equations in an inexpensive laptop in 10 minutes. So after 10 minutes, you can get all the variables that are needed for calculating microstructure, properties, and common defects in additive manufacturing. Let me give you some examples. So let's say you are simulating directed energy deposition, and this is the deposit, and I am taking here half of a deposit for symmetry. So this is the temperature field, which is compressed in front of the molten region, and it is elongated in the opposite to the scanning direction. And you can see that because of the accumulation of powder particles, it forms a curved deposit. And if I zoom into the molten region, you can see that temperature is the highest in this region where we have the laser beam, and it gradually decreases as we go away from the center of the laser beam. So temperature is the highest here, and temperature is lowest, which is the solidus temperature for the alloy at the boundary of the molten pool. So now we know from our high school physics book that surface tension is the lowest where temperature is the highest, and surface tension is highest where temperature is lowest. And fluid flows from high surface tension to low surface tension. So you can see that there's a flow from this location where surface tension is low towards where surface tension is high. So you can see the flow of the liquid metal along the curved surface of the deposit. And this flow actually redistributes the hot and cold liquid inside the molten region and redefine the temperature field, which as a result control the cooling rate, control the temperature gradient, and resulting microstructure. So how the molten pool looks like for powder bed fusion? It's like, in powder bed, you deposit thin layer and the powders are spreaded by using a roller. So the top surface is almost like a flat plane. And as I was mentioning previously, that you can see the temperature field is stretched in the opposite to the scanning direction. But in contrast, if you go to DD, you can see the deposit is not flat on the top surface. Instead, it's curved. Why that is so? Because it is formed by accumulation of powders. And you can see the velocity field is also following the curved surface, the curved top surface of the deposit. So on the top surface, the velocity has all three components, x, y, and z. Same thing you can see for gas metal arc based DED, but the deposit is little different. The arc creates a high pressure on the top surface of the molten pool. So it kind of pushes the liquid metal from this region to the backward, and this elevation actually forms the curved surface of the deposit. Also, in DDGMA, the molten metal from the electrode drops, and because of its weight, you can see there's a finger-like penetration. So both the processes actually work together to define the shape and size of the molten region or the deposit for directed energy deposition GMA, which is also called as wear arc additive manufacturing. But for in this case also you can appreciate that the molten metal also flows along the curved surface. But What if we compare these three processes? We will see that there is a significant difference in the shape of the molten region, as I was explaining, but also at the same time, there is a significant difference in the size. For GMA arc-based process, the energy density is very high, and that's why the resultant molten region is much larger compared to the other two processes. In the other hand, for powder bed fusion laser, where we deposit very thin layer in the micron range, often thinner than human hair, so it forms a very small, tiny molten pool. So if we want to make a very complex and intricate part, we need to deposit very thin layers. We use powder bed fusion. But if you want to make a structural materials where you do not worry that much about the surface finish, high productivity is the concern, you use directed energy deposition gas metal arc process. So the bottom line is this model can guide you to select the process for your particular application. So you can see that it can simulate the molten region or the deposit for three processes, which is very consistent with the experimental observation. So for same material, this is for stainless steel 316, you can see the modeling result actually matches very well with the experimental observation. Apart from the deposit, the model can also give you the variation of temperature with time for a particular location. We call it thermal cycle, this one. And also the cooling rate, which is a very important parameter for predicting the microstructure. How good the calculated results are compared to the experiment. So let's say you are depositing one thin layer on a top of a substrate and you put a thermocouple at location A, which is little bit away from the deposit because it's very difficult to measure temperature using a thermocouple accurately inside the deposit. So this is for H13 tool steel, and you can see that the computed result match reasonably well with the experiment. So why we need the validation of model result? Because it will provide us the confidence that we can use this well-tested model for predicting microstructure properties and defect. So the bottom line is the model can give us the temperature field and cooling rate, also the solidification morphology, whether this is columnar or equiax, the grain structure in 3 dimension, residual stresses, which is one of the major concern in any manufacturing processes, and also defects such as lack of fusion, porosity, cracking, so on and so forth. So now let me give you examples that how the models and machine learning can be used for controlling grain structure, properties, and defect. Now, as we know that in additive manufacturing process, solids are formed from liquid, like any other process like casting or welding, so on and so forth. But for alloys, solids do not form directly from liquid. There is a two-phase region, as we see from the phase diagrams, solid, liquid, massy region. So if we look at the massy region, we can see that the equilibrium liquidus line is away from the actual liquidus line. So this region, as we know from phase transformation book, it's called supercooling. So two parameters, one is the temperature gradient delta T and the other parameter is the growth rate R. These two parameters control solidification morphology and the grain size. So if we plot temperature gradient versus growth rate, the slope of this plot, which is G by R, can give us the solidification morphology. So whether this is equiax dendrite, columnar dendrite, cellular or planar. Generally for additive manufacturing, we see columnar dendrite and equiax dendrite. So there is a threshold for each alloy of G by R beyond which it forms columnar dendrite, and below which it forms equiax dendrite. The product of temperature gradient and solidification growth rate, GR, it determines the solidification structure size. So we can calculate the cooling rate, and from which we can see how big or how small our solidification structures are. So let's see how to control the solidification morphology. As I was mentioning that there is a critical G by R for all alloys. So here the example is for wire arc processing of an aluminum alloy 6061. So the critical G by R is 9 Kelvin second per millimeter square, above which it will form columnar grains, below which it will form equiax grains. So we can calculate the value of G by R along the molten region. So you can see that beyond, let's say, 1.5 millimeter, the calculated value of G by R is above 9 Kelvin second per millimeter square. That means it will form columnar dendrite. It is very much consistent with the experimental observation. And in the other region, where the G by R is below the critical value, which is 9 Kelvin second per millimeter square, our computed result tells us that it will form equiax grains. And that is indeed true when we see the experimental result. So it's not a magic. So we can do the calculation, and before doing the experiment, we can see whether it will form the columnar grains or equiax grains. Now, both G and R we can control during the experiment by adjusting the process conditions guided by the model. So if we do not like the columnar grains, which is detrimental for tensile properties, we can adjust processing conditions guided by model and achieve a fully equiaxed solidification structure. Now let's say we form columnar dendrites. Now there are many features of columnar dendrites, like let's say there are two Christmas trees, two columnar dendrites. The distance between their tip is called primary dendritic arm spacing. But each of the columnar dendrites have many small secondary arms, and the distance between two consecutive secondary arms is called secondary dendritic arm spacing. And it has been found that this secondary dendritic arm spacing has significant effect on tensile properties. So how we can calculate secondary dendritic arm spacing from cooling rate? So there is the formula. You can calculate the cooling rate, which is the product of temperature gradient G and solidification growth rate R. Now these two constants, 50 and 0.4, they depend on alloy. So this is for stainless steel, but if we change the alloy, let's say nickel alloy or aluminum alloy, they will change. And there are handbooks that have values for these two constants for different alloys. So what we get, we for different laser power, we run the code, we calculate the cooling rate, put the cooling rate in this formula, and calculate the secondary dendritic arm spacing. And then when we do the experiment, we see it match reasonably well. So the bottom line is, you can actually use this kind of model to control the solidification structure and their size. And at the end, you can control the properties. But solidification structure is not the only factor that control property. Let's say we take a very simple property, hardness of ferritic steels. The hardness of ferritic steel is affected by martensite. So this is a CCT diagram of a ferritic steel grade 91, which is commonly used in nuclear power industry. You can see that martensite forms at a very low cooling rate of 0.05 Kelvin per second. So which is significantly low compared to the typical cooling rates that we see in additive manufacturing, which is like 10 to the power 4, 10 to the power 5 Kelvin per second during the solidification. And the martensitic start temperature, which is also quite high compared to the room temperature for this particular alloy. So when the part cools down to the room temperature, it will form the martensite. But in additive manufacturing, we make the part by depositing layers. And when we deposit many such layers, that means we are repeatedly heating and cooling the part. And this repeated heating and cooling tempers the martensite and forms tempered martensite, which will completely change the final mechanical properties of the part. How we can predict that? So we need two things. One is the repeated heating and cooling, which is the variation of temperature with time. We call it thermal cycle, and a very good understanding of the tempering kinetics. What we need to do, we need to generate tempering data, which is nothing but variation of hardness with respect to time for different aging temperature. Now, for all materials, it's very difficult to generate the database. So what is an alternative is take the data-driven approach. So collect the data from literature for different aging time and temperature, train a neural network, and then use the trained neural network to generate high quality aging data. So see, here is the benefit of data-driven tool. When we do not have the data, we have a limited set of data. We can use that, train this kind of machine learning algorithm, and generate reliable data in a large quantity. Then use the data and find out the constant in Johnson-Mehl-Abrahami equation, which is a very well-known equation to represent the tempering kinetics. On the other hand, use the heat transfer fluid flow model that takes the process condition and alloy property and accurately gives us the temperature variation with respect to time. And these spikes are for individual layers. So you can appreciate the repeated heating and cooling during the multi-layer deposition. Integrate the JMA equation, which is essentially an isothermal equation, along this thermal cycle and calculate the hardness of the part. How? Let me show you. So for directed energy deposition laser of grade 91 steel, the calculated hardness variation is shown using the red triangle, and corresponding experimental measured values are shown using blue squares. They are matching reasonably well, but one thing we should observe that after a certain layer, there is no appreciable change in hardness, but below which you can see a linear change in hardness. Why that is so? Why there are two trends? For this yellow region where the hardness is gradually changing with distance, let's look at the thermal cycle. I have indicated the AC1 temperature. Above the AC1 temperature, it forms austenite. So let's consider the first layer. The temperature is increasing. It is above the solidus temperature and liquidus temperature. It melts and then it rapidly solidifies and cools down. During that process, it forms martensite. But the same martensite transforms to austenite again because the temperature goes above the AC1 temperature. And then it forms martensite again, austenite again, martensite again. But after some time, you can see that the temperature of that location does not go beyond the AC1 temperature. And after that moment, the martensite that it contains will undergo repeated heating and cooling below the AC1 temperature, which will change the martensite to tempered martensite, and which will significantly reduce the hardness. So you can see that for the layer 1, the hardness is very low, but if we consider, let's say, layer 3, which will have less number of repeated heating and cooling below AC1 temperature, so its hardness is reduced, but not like layer 1. But if we see the upper layers, you can see that for 8th layer, this is the spike. For 9th layer, this is the spike. And for 10th layer, this is the spike. So it is not getting any opportunity where it can undergo the martensite to tempered martensite transformation. So in this region, the hardness is always dominated by martensite. And that's why it's not varying that much. So two region, and we can fully explain the hardness of these two region depending on the calculated thermal cycle and tempering kinetics. And the most important thing is we can adjust the process parameter guided by this type of model to control the hardness variation. So the extent of tempering of martensite also follow the similar trend, but in the opposite way, because more it tempers, the hardness change more. So where the hardness does not change, we do not see any change in percentage of tempering. But not only the microstructure or phases control the final mechanical properties of the part, there are several defects that also contribute. One of the most prominent examples is lack of fusion void. Imagine your printed part has a lot of voids. It will never have a good tensile properties. So, how to control lack of fusion void? We start from the well-known three-dimensional temperature and velocity field from which we extract the molten pool. So I am showing a view in 3D so that we can also see the internal surfaces of the molten pool. Now, please look at this transverse section, which is perpendicular to the scanning direction. Now, zoom it and you will see the cross section of the deposit, which looks like half of a watermelon. And you can see the velocity fields also from the center to the periphery of the molten pool. Now, in additive manufacturing, we deposit many such layers. So let's stack this type of molten pool for different layers and hatches. The white regions among the consecutive stacks is the origin of lack of fusion void, this white region. So your question should be how we can minimize this white region. You can say, okay, bring the two watermelon closer. That is true. The distance we called as hatch spacing. So if we reduce the hatch spacing, this area will be reduced and lack of fusion defect will also be reduced. When we go to the shop floor, do the experiment, exactly that is true. At lower hatch spacing, void fraction is significantly reduced. So before even we do the experiment, model can guide us which process parameter we should select for reducing such defect. What are the other ways to reduce the white region? You can probably go slowly. Your scanning speed, if you reduce, that means per unit time, you are depositing more energy at the same location. That will melt more material. So your size of the watermelon will be significantly increased, which will reduce the white region. That means if you scan slow, you can effectively reduce the lack of fusion, which is also consistent with the experiment. When we go to the shop floor, do the experiment, we can find exactly the same story. For different alloy, lack of fusion also form differently because it is not only the process condition like the heat input, but also the material property. Let's say you have one alloy that has very low density. So for the same heat input, it can melt more material because of its low density. Let's compare stainless steel and aluminum. Aluminum has almost one-fourth of the density of stainless steel. So the amount of molten region is significantly larger compared to stainless steel. So for the same processing condition, aluminum silicon tin magnesium alloy is less susceptible to lack of fusion compared to stainless steel. So this is a combined effect of process parameter and alloy properties that can be revealed only by using phenomenological understanding captured by mechanistic modeling. So if we know all the parameters and somehow try to combine them in a dimensionless form, that would be very useful for predicting lack of fusion defect in soft floor. So let's say we do not have the luxury to run a lot of model. We can probably use a back of the envelope calculation based on this type of dimensionless formula and can know what works and what does not work in terms of lack of fusion. So it has head spacing by width. So if the head spacing is same, if we can melt more material, that is beneficial for reducing lack of fusion. But if we have the same width for the same material, if we increase the head spacing, we increase the lack of fusion. So like that, the ratio of layer thickness to pool depth, the power density, which is a combination of laser power, absorptivity, laser beam radius, and scanning speed. So if we reduce the energy density, it will melt less material and increase the lack of fusion. This is density times specific heat delta T plus latent heat, which is nothing but the energy required to melt per unit volume of material. If we need more energy, that means we will form small molten pool and it will increase the chance of lack of fusion. So combine all the important variables and see whether you can actually predict what happens during the experiment. And here you can see that this LF, which is the lack of fusion number, has a linear trend with the experiment. So before if you want to do experiment, before you can do the experiment, using this kind of analysis, you can tell whether you will have a lot of lack of fusion or your product will have no lack of fusion. So when we know all the variables, we can also take the benefit of machine learning. And machine learning can tell us which variable is the most important and which variable is the least important. For example, here it tells us the ratio of pool width by head spacing is the most important variable. And when we try to gather all the experimental data, and here I have 120 data for 4 commonly used alloys that we use for additive manufacturing. You can see that this most important variable can actually give us a threshold above which all experiments are good. You can see the microstructure, and below which all experiments are bad. Your product is looking like Swiss cheese. So if you want to have a very good product, you want to be in this region. So before you do the experiment, you can have some understanding that which route you need to follow for becoming successful. Residual stress is another problem. Now, calculating residual stresses is not a difficult task because nowadays there are many commercial packages like ANSYS or Abacus that can calculate residual stresses with a very high technology readiness level. But there is a small issue. We know that the convective flow inside the molten region can significantly affect the temperature field, and finite element based packages cannot capture that effect of convective flow. So at Penn State, we actually started from the heat and fluid flow model, calculate the accurate temperature field by considering the effect of convective flow, and then export the temperature field along with the geometry and mesh to a commercial package Abacus, which effectively calculate the residual stress, strain, and deformation accurately. So this kind of calculation actually tells us how a part distorts or how residual stresses are accumulated during additive manufacturing process. So distortion is nothing but accumulation of strain, which is very well known beta delta T. So you can see that where the temperature is higher, that's the location where strain or distortion is being accumulated. With the progress of the process, where the laser beam moves from this location to this location, you can see the higher amount of strain accumulated along that line. So for strain and distortion also, we can do back of the envelope calculation. Only thing we need to have is the phenomenological understanding of how distortion occurs and the variable that affect the distortion. For example, beta delta T, which is proportional to distortion. Heat input. More heat you deposit, you will increase the temperature and you have more distortion. Flexural rigidity. Young's modulus times area moment of inertia. That is the strength of the material. That means if we have high flexural rigidity, the part will be rigid enough to prevent the distortion. Like that, we have many variables that either affect the strain in positive way or in negative way. So when we know all the variable, we can use simple things like what we learned in second year mechanical engineering class, Buckingham pi theorem based dimensional analysis. We can use those and form a dimensionless number to represent strain. And you can see that experimentally measured strain follows a linear trend with this number. What are the advantages? We can use that strain parameter and compare the distortion among different processes. Let's say arc-based process, laser-based DED, and powder bed. So for powder bed, our molten pool size is very small because we use very small heat input. You see the laser power here and scanning speed. They are the heat input, which is nothing but the laser power divided by the scanning speed, is very small compared to the other processes. So the pool volume is small, smaller pool shrink less during the solidification and distort the part less. So that's why you can see the strain parameter for powder bed is significantly less compared to other processes. In the other side of the spectrum, we have gas metal arc based process, where the power and the net heat input, which is power by scanning speed, is very high. That creates a very large molten pool, which shrinks more during the solidification process and accumulate a high value of strain. So if we take the same process, let's say DED, and compare among different alloys, we can see that depending on the alloy properties, the thermal strain is very different. For example, let's say titanium alloy, which has less density compared to stainless steel, which will form larger molten pool, shrink more, and accumulate larger strain compared to stainless steel. So if you see this first, second, and third, these are layers for 3 layers deposit. For first layer, if you compare between stainless steel and titanium alloy, you can see for titanium alloy, the strain is higher. Now, for a particular alloy, if we go up, that means you are going away from the substrate. And as you know that in additive manufacturing, heat flows from the molten pool through the substrate. So if you go away from the substrate, the rate of heat conduction is less. That means you are accumulating more heat, that is generating a larger molten pool, which will increase the susceptibility to distortion. So as we go up, the strain or the distortion also increases. In contrast, if we go slowly, we form smaller molten pool, which is beneficial for reducing the thermal strain. And here, if you compare all the alloys, aluminum alloys, because of its low density, it forms the largest molten pool among these four common alloys, and it has the highest susceptibility to strain and thermal distortion. So this kind of calculation actually give us some idea of printability, which is nothing but the applicability of a particular alloy to additive manufacturing. So if we can kind of think that, for a particular alloy, if we want to use DD, whether it's very susceptible to distortion or very susceptible to other defect, then we cannot probably use that. So that's what printability. So how to mitigate distortion? As I explained, that either you increase the power, either you decrease the power to reduce the molten pool size, increase the scanning speed, or you arrange your layer number or layer thickness in such a way so that you can minimize the thermal distortion. Residual stresses. We need to understand how stresses evolve during the process. So let's imagine that we are making a thin wall on the top of a substrate. And please note this yellow dotted line. This is the path along which we are extracting the temperature and the residual stress. Now, residual stress is a vector. It has three components. So when I say longitudinal residual stress, that means the component of the stress along the scanning direction, which is along the x-axis. So at t equal to 0, just after it finishes the deposition, temperature is the highest here in this location, because the laser beam moves from this location to this location, because the scanning direction is this. So at the end of the deposition, the temperature is the highest here. So material is the softest, and we know soft material cannot accumulate residual stress. So you can see the residual stress is the lowest here. But as the time progresses, the temperature drops down, shown by this green line, and you can see that the stress is also increasing. And at the end, let's say after 50 seconds, where the temperature is almost like the room temperature, we have a well-developed stress field, which we call residual stress. Now, at the two observations. First, you can see that when the second layer is finished, there is a high residual stress accumulated near the top of the deposit. But when we deposit the third layer, this residual stress is partially alleviated because of the reheating and recooling. And then at the end of 10th layer, you can see the observation is very similar to second layer. At near the top of the deposit, where we have the highest amount of residual stress. But after the deposition of second layer in this location, the high amount of residual stresses is partially alleviated. Second observation is, you can see at the layer interface and also near the substrate and deposit interface, the residual stress is sharply changing from tensile, which is positive, to compressive, which is negative. And this sharp change often causes the separation of the component from the substrate, or delamination. How well the calculations are, I also took two examples along AB, which is along the deposit, and along CD, which is along the vertical direction. And for both cases, the experimental measurements were done for through thickness residual stress. So through thickness component is along the vertical direction. So along the longitudinal direction, longitudinal stress, along the width direction, transverse stress, and along the vertical direction, this is called through thickness residual stress. So in both cases, you can see that the residual stresses measured using hole drilling technique match reasonably well with the computed result. So it gives us the confidence that we can use this type of calculated result for predicting defects such as delamination. Residual stresses also vary significantly for same alloy if we take different processes. For example, let's say for powder bed, since we deposit very thin layer, the stress accumulation is quite less. But in contrast, for gas metal arc-based process, where we deposit a lot of material which accumulates higher residual stress, as you can compare here, for same material. But if we change the material for the same process, let's say laser-assisted directed energy deposition, you can see titanium alloy accumulates more residual stress because it has higher yield strength compared to nickel alloy. So not only it can compare the susceptibility of stress accumulation for different process for same alloy, but also for same process, it can compare different alloys. So once again, it can tell you that this kind of calculation can help us to evaluate the printability of different alloys. So I was mentioning about delamination, which is separation of the part from the substrate. So let's take the longitudinal residual stress along the deposit substrate interface, because that's the stress we are interested in, because we want to see the change between the residual stress in the component and in the substrate. We are comparing two alloys. For titanium alloy, the residual stress is quite high because of its higher yield strength. But delamination is not only dependent on the absolute value of the residual stress. It also depends on the yield strength, particularly the room temperature value of the yield strength, because this is the strength of material that will prevent the separation of the component from the substrate or prevent the delamination. So if you take the absolute value of residual stress, divide it by room temperature yield strength, that is the index you are looking at. Higher value of the index, higher chance of delamination. Although titanium alloy, indicated by blue, has very high absolute value of residual stress, but because of its high yield strength, the delamination index is less compared to Inconel. So, although titanium alloy forms higher residual stresses, but it is less susceptible to delamination defect. So, this type of calculation can also guide you to do process design. Let's say you are making a rectangular block. Now you can make it in three ways. You can scan along the longitudinal direction, or along the shorter direction, the width direction, or instead of scanning in a linear path like these two, you can scan in a spiral path. So which route you can take, because depending on which route you take, your productivity will be changed. But the stress accumulation in these three parts are very different. You can see if you take the shorter route, your residual stress accumulation is significantly less compared to the other two routes. So not only it can compare different processes, different materials, and help us to evaluate printability, but also it can guide us to design the process and improve productivity in real practice. Also, if we take the calculated result and give that result in machine learning, it can tell us which variables are more important and which variables are less important. For example, let's say if we fit the calculated residual stress for three alloys using a random forest based machine learning, it can tell that the delta T, which is nothing but the difference between solidus temperature and preheat temperature, is the most important variable. And this is not a new science. If we go back to the fusion welding literature, we always see that welding practitioners preheat the component to reduce the residual stress. So if they preheat the component, they are nothing but reducing the delta T, which is the most important variable for controlling residual stresses. So essentially, here is the interesting thing that we are synthesizing the data coming from model and machine learning for a new emerging field of additive manufacturing, and we are finding out same technology or same scientific fundamental understanding that is developed probably 40-50 years ago, experimental trial for fusion welding. So, residual stresses or stress evaluation can also affect in many other ways apart from delamination. One of the example is solidification cracking. How? Let's imagine that during the solidification, grains are growing. Now, if these grains are undergoing very high amount of tensile stress, then they will start separating from each other, and that is the origin of crack. Not only the stress, there are other factors like ratio of vulnerable and relaxation times. This is these two times represent how the solid forms in two-phase region in the massy region during the solidification. Temperature gradient to solidification growth rate ratio G by R, which represent the solidification morphology as we saw, and obviously the cooling rate, which is nothing but GR. So if we have all these four variables, feed them in a very simple linear regression, we can derive a crack susceptibility index, and the magic is it can also give us a delineation above which all experiments show crack, below which all experiments are good with no crack. So even if you do not do the experiment, you can have the way to use a very user-friendly, verifiable crack susceptibility index to figure out whether for your alloy, for your condition, crack will form or not. Not only that, it gives us other benefit. It gives us which is important and which is not important. So to calculate hierarchy, generally people use several index like information gain and information gain ratio, and we have described this in detail in our recently published acta material paper. So what we have found that solidification stress is the most important variable controlling solidification cracking. So this is the variable we want to control at the first step to reduce solidification cracking. Another very important defect that we often underestimate is composition change. So let's imagine you have a coffee cup. So the water molecule vaporize from the top surface of the mug. Like that, during the welding or additive manufacturing, the alloying element vaporize from the top surface of the molten pool. But all elements do not vaporize at the same rate. And these selective vaporization actually cause a significant difference in the composition in the final part compared to the part we start with. For welding, you can see for laser welding of aluminum alloy, in the welded region, the magnesium concentration significantly reduced because of the evaporation compared to the base metal. So this observation is also true for additive manufacturing. And how we can model it? So for modeling it, we need to know the temperature in the top surface, like this. And then we have vaporization model. Now this vaporization model can vary depending on the complexity. It can be a very simple Langmuir equation based calculation or a complex Knight's model that was developed in Russia and eventually developed in many stage and then eventually used in welding and additive manufacturing. Another thing you need a database of vapor pressure versus temperature for alloying elements. Now, as I was saying that the vapor pressure does not change with temperature equally for different alloys. Another thing is when the vapor pressure is equal to 1 atmosphere, if you draw one horizontal line for one particular element, the corresponding temperature is the boiling point of that element. So boiling point is not the same, vapor pressure is not the same. That means they do not vaporize at the same rate. And this selective vaporization is the root cause of composition change. So we take the database from literature or any handbook, combined with the vaporization calculation, then we can know the vapor flux for individual element. And what is the benefit? We can calculate the composition change for individual elements. Then we do EPMA to figure out what is the composition at the final part and see they match reasonably well. So it seems very complex process, but with the help of the model, actually we can tailor the process conditions and prevent this kind of undesirable composition change. We can completely change the phase formation and final microstructure. Composition change actually depends on a factor which is nothing but the ratio of pool top surface area by pool volume. So higher top surface area means more vaporization that will change the composition more. But at the same time, composition is changing from how much material. To represent that we have pool volume. So if same amount of material is vaporizing from a very large molten pool, composition change will be very less. That's why it is indirectly proportional. For powder bed, although the pool top surface area is very small, the net amount of vaporization is less, but at the same time, powder bed has the smallest molten pool. That's why among the three processes, it shows the highest amount of composition change. So it has the highest amount of top surface area by volume ratio. That is the reason of the composition change. So if we have the same material and same process and try to compare different common alloys, we can see that for titanium alloy, aluminum is the most susceptible element for vaporization. For stainless steel, this is manganese. For other steel also, this is manganese. For this Inconel super alloy, this is chromium. Although the most susceptible element for vaporization vary for different alloys, their amount of composition change also significantly vary depending on which alloy we are using because of their very different vapor pressure versus temperature behavior. How to reduce the composition change? We need to reduce the top surface area by volume ratio. And a very easy way to do is by doing a proper selection of heat input. And it works for all three processes. So lower heat input means lower composition change. And this is very consistent across different alloys. So our last defect for today is surface roughness. Now, as we know that we often need to make very complex and intricate parts like medical implant. And you can see that we need to have very high surface finish for the femoral stem and tibial head, this part. So since these days we make this kind of implants using 3D printing, surface roughness is a major concern. So you see that this is the as printed implant, and this is the implant that actually is used after post processing. But this kind of post processing can only be done for the external surfaces, not like the internal surfaces inside the head. And also, it will add cost to an already expensive process of additive manufacturing. So, how to reduce that? We can probably print this part with very small layers using powder bed, let's say. This is consistent with the experiment that if we print the part using thinner layer, surface roughness is reduced. But not only the layer thickness, which increases the staircase effect and eventually the surface roughness, but there are many other parameters. For example, here I have listed several of them, like enthalpy of melting, layer thickness, molten pool, aspect ratio, contact angle, so on and so forth. And using a dimensional analysis, we can combine all the parameters into an index, and you see that there are many experimental data for 4 commonly used alloy, and the surface roughness follow a linear trend. High value of index, like here, surface is very bad. Low value of index, here, surface is quite good. So this kind of index can tell you how the surface would look like of the final part even before doing the experiment, so that we can actually adjust our parameter, minimize the index, and then take that parameter, go to the shop floor, and print the part in one go, absolutely magnificent way. Balling defect is another defect which forms small balls on the top of the surface, and that creates surface roughness. So using machine learning, we have identified that there are two important variables, Marangoni number, which represent the flow behavior, and the solidification time, and both the variables can delineate between the good cases and bad cases. Good cases means no balling for all the alloys, and bad cases means balling, which is a source of surface roughness. Now you can ask me that, okay, Tuhin, you have talked about using machine learning. How we can use machine learning? And here I have taken this table from our recently published review paper in Nature Reviews Materials, where we have listed several open source programs that you can freely download from these websites, install in your computer, and do any type of data-driven analysis for additive manufacturing and for other different applications. For example, this Weka is a very widely used open source software from a university in New Zealand that is widely used for a wide variety of applications in additive manufacturing, that you can freely download, install in Linux-based, Apple or Windows-based computer, and it comes with extensive manual that will help you to download, install, and use that for your applications. So what are the major contributions of this work? Definitely, it provides methods based on fundamental understanding to control grain structure and solidification morphologies, which can be tested against experiments and which can also guide us to improve the microstructure of additively manufactured part. Ways to reduce spatial inhomogeneity of mechanical properties like tensile strength, hardness, so that we can improve the quality, reliability, and serviceability of the component. Minimize the common defects like lack of fusion, surface roughness, distortion, so on and so forth, so that our product does not need to undergo expensive, time-consuming post-processing, and we can make the desired part in one go. That's way that is the way to reduce the cost of additive manufacturing and improve the market penetration of additive manufacturing. But the most important thing is this can provide us improved scientific understanding of an emerging process, and the scientific understanding of evolution of structure, properties, and defects that cannot be obtained easily and economically in any other way. But you can ask me, so what is the futuristic viewpoint from here? Where we can go from here? One thing we can say is constructing a digital twin. What is a digital twin? Digital twin is a digital replica of the physical hardware. For our case, the digital replica of the additive manufacturing machine. General Electric, which is the largest producer of aircraft engine, uses 5,500 of digital twins. That means digital replica of their actual aero engine to monitor which part works and which part does not work. We can take that idea and eventually construct a digital twin for additive manufacturing. We published this idea in Applied Materials Today few years ago. Essentially, the idea is it has to have some essential components. Combination of mechanistic, statistical, and control models, data-driven tools such as machine learning, and a big database that will have the simulation data, testing result, all literature data, and the sensing and control data obtained during the experiment, so that we can synthesize all the data using the data-driven tool and improve the model so that we can continuously improve the quality, serviceability, and reliability of the part and make additive manufacturing better. So these modeling, machine learning, big data analysis need a lot of computational effort. Where we can go in the future? Quantum computing is a futuristic viewpoint. So IBM is also saying that quantum computing, their IBM Qiskit quantum computer, which they have already made freely available up to 5 quantum bit. You can go to this website, just Google it. You can go to this website and you can get free access of 5 quantum bit quantum computing facility where you can run any computing code written in Python. So that's the opportunity. So they are saying that this is the future where we can use quantum computing and develop breakthrough products and services that will redefine the manufacturing, including additive manufacturing. Small business innovation research in the US that fund small startups in the US, they are also saying that quantum computing is the future of 3D printing, not only in the US but worldwide. So quantum computing is the future that has the potential to reduce a lot of the computational burden. So what is the broad impact of all of these? Mostly, it will give us a new path for cost-effective and rapid manufacturing. Today we are doing additive manufacturing, but down the lane after 20, 30 years, use of digital tool can help us for rapid development of new manufacturing processes. That would be very different from the traditional manufacturing processes like welding or casting that were developed mostly by doing experimental trial and error. But for new manufacturing processes, they are expensive, so we do not have the luxury for doing the trial and error. And in those cases, virtual test using digital tools is the future. And also, I believe that the research using digital tool can break the accessibility barrier. So anyone from anywhere in the world can contribute to the research. They need to just have an inexpensive laptop, and a stable internet connection. And in using digital tools, they can contribute to the research, and that will create an welcoming and equal research opportunity worldwide. So that's all I had.